morning, everyone. Nice and cold out there, so no herbicide degradation occurring today. I can guarantee you that. So basically I want to talk about for the next half hour some of the just kind of concepts when it comes to herbicide degradation, and then looking forward to 2022, some of the top products or active ingredients of concern on my mind that we might want to look out for as far as carryover concerns into our crops next year. So first, I figured it would be nice to take a look at where we're at today. So this is outdated by week. Here's the updated drought monitor. And so I'll be honest, I haven't really looked at this since back in the summer, so I was kind of surprised to see the southeast corner of the state was taken off completely. Here we're kind of in the abnormally dry, so I guess we had enough of this fall rain, or at least as far as the drought monitor is concerned. We've basically been taken out of drought status at least, and just kicked towards abnormally dry. So it can be a little deceiving. You look at this, you might think, we're maybe back to normal-ish. Carryover may not be concerned, but if this is what the map looked like in August, then we wouldn't be talking about this topic today. Instead, here's what the map looked like at the end of August. And so I point this out because historically we basically always say that most herbicide degradation occurs June, July, and August. When it's warm soil temperatures and we need moisture to drive degradation as well. So we really look at those peak summer months for most of our herbicide degradation because that's when we have the heat and we typically have the moisture to drive degradation. Of course, this past year we didn't have a whole lot of moisture during the summer months. I'll talk a little bit later about the fact that we did have quite a bit of moisture in September and pretty warm temperatures. So we probably got more herbicide degradation this past September than many Septembers in the preceding years because of the warm, wet conditions throughout September, but still the primary herbicide degradation months just did not get the rainfall for most of the degradation we would typically want in a year in and year out basis. So one thing that I'd like to address when we talk about just carryover concerns in general is we do have to take a little bit of time to talk about the fate of a herbicide after it leaves the nozzle of the boom. In this case, we're going to say the fate of the herbicide once it hits the soil. And oftentimes we might get asked about a marginal active ingredient carrying over to a crop next year, and you might get an answer of, well, maybe, or it depends, and it's because the whole system is pretty complex. So that cartoon up there does a pretty good job, I think, basically highlighting all the different ways that herbicides degrade or all the different fates in the environment. Photo decomposition, so breakdown by the sun. We can have runoff, of course, leaching, in worst cases, leaching all the way to the water table. Uptake by crops and weeds is probably the ultimate fate we want. So the crops would detoxify the herbicide, the weeds would hopefully die after they absorb them. And then basically the herbicide that's not lost to all these different arrows leaving the system is the herbicide that's left remaining that we're concerned about that needs to be degraded so we can plant our crops safely the next year. So, 3 general processes I'd like to talk about with herbicide degradation. Again, this is kind of once the herbicide hits the soil. First one will be absorption, so the herbicide itself attaching to soil particles. And so in this case, the herbicide is not actively available in the soil water to be uptake or leach or run off or do whatever. So it's bound to soil particles. Movement of the herbicide, so this is runoff, leaching. We have some tile flow, there is some volatility of some of our soil-applied herbicides, and then plant uptake again as well. But mostly today we're focusing on degradation of herbicides, the processes behind degradation, and why we had some degradation occur and some not occur this past year. So 3 main processes within degradation we're going to talk about: photo decomposition, microbial, and chemical. But before we get to the degradation processes, I'm going to talk a little bit about chemistry. I really want to focus on the half-life of a herbicide. And so this is basically the amount of time that, and this is for herbicides, but really any chemical compound in the environment has a half-life. It's the amount of time it takes for that half of that chemical to degrade in natural conditions. And so on this figure here, we have on the x-axis just numbers 1 through 6. We'll pretend like those are months. So this is the half-life by month of a herbicide. And so if we apply the herbicide at time 0, 100% of that herbicide is available in the soil. 1 month later, only 50% is remaining, so it's gone through 1 half-life. And this is a logarithmic scale, so then the next half-life, 50% of what is remaining gets taken away. So 2 months later, we're down to 25% left of the original application. And so again, logarithmic scale, But just an important concept to remember with half-lives is that some herbicides have very long half-lives, so take a long time to degrade, and then others have much shorter. And now it's out on the chart a bunch of our different typical herbicides we might use year in and year out. Some of their half-lives to show you basically the variability or the variation within individual chemistries that we use. So at the top, the three up there, we have dicamba, Eptan, and 2,4-D. And these are relatively short-lived herbicides. If we apply them in the spring or summer, we're really not concerned about carryover the next year. Part of that is driven by the chemistry. So dicamba has an average half-life of 5 days. So basically, if you apply half a pound dicamba, in the average conditions, 5 days later, there's only a quarter pound that's left in the environment. And then, again, goes on that logarithmic scale. Compare that to one that we're probably concerned on an annual basis with atrazine. We know it can be quite persistent in the environment. Atrazine has a half-life of 60 days. So if you apply half a pound of atrazine on June 1, come August 1, there's probably still a quarter pound left in the environment on average. So again, just showing chemistry, just based on the half-life of the active ingredient itself, will have these differences in persistence. Where this can come into play in environmental conditions, of course, a high or a low rainfall year does affect degradation. High rainfall years, constantly saturated soils, we get enhanced or increased degradation. So now the black line is still that herbicide from 2 slides ago with a 1 month half-life, now it's changed to days. The blue line is the high rainfall environment. So now, if we're in a high rainfall year, half-life might be, looks like about 20 days in that chart. When we get to that 30 days, rather than 50% remaining, only 25% is remaining. So much more enhanced degradation in wet years. 2021 is more like the red bar. So dry years, when we don't have saturated soils, we don't get the degradation, the half-life does then increase because we're not getting degradation. So in general, all of our herbicides we apply will persist longer because we're not getting the degradation. So environment does influence half-life. So when we talk about half-life, it's usually the averages. So dicamba was a 5-day average across all environments, probably a little bit longer in 2021. Where this comes into play is actually the crop sensitivity when we talk about carryover specifically. So one example I like to always pick on is famecifin, which is Flexstar or Reflex. If you look at the label, it's a 10-month rotation restriction to corn, 4 months to small grains. So the other thing we always have to remember is that the dose makes the poison. And so if we're looking at famecifin carryover, basically what we want to do is degrade enough of that chemical that we have we have less in the soil than we would need to cause injury on the crop. And so that's basically the goal. So we can always have years where we still can detect herbicide residues in the soil, but if it's not enough to cause injury to a crop, then we're going to be good, safe to plant the crop, and we're going to be okay. So it's really all about degrading herbicide below the crop sensitivity threshold is really the concept we need to think about. Okay, so as far as degradation, the 3 general processes, going to quickly touch on the first 2. So photodecomposition is basically breakdown by the sun, breakdown by UV rays. Many of our soil-applied herbicides are actually relatively UV stable. There are a few, though, that are very sensitive to the sun and break down rather quickly. The classic example, some of our yellow herbicides, Trefland is really the classic example, is very sensitive to the sun. So one of the reasons we incorporate Trefland within 24 to 48 hours after application is because it's very sensitive to the sun. We can lose quite a bit of Trefland quickly just due to UV breakdown. So again, most herbicides not really impacted by UV breakdown, but Trefland is a classic example. Chemical degradation, very important. There are a couple different processes on the screen there. We're not going to talk a whole lot of chemistry today, but I would just say that hydrolysis is the number one reason for chemical breakdown. So again, there's some other reactions on there, but hydrolysis really is what drives chemical breakdown of herbicides. But by and large, it's microbial breakdown that's the most important process for herbicide breakdown in the soil. In microbial breakdown, that's just all the different microbes in the soil, bacteria, fungi, actinomycetes, at least 6 or 7 different enzymatic ways that they actually break down herbicides. by cleaving off chains or breaking open benzene rings, just a number of different processes that the microbes work on the herbicides to degrade them and make them no longer toxic. Again, we're not going to talk the hard chemistry here, just showing all the different ways that microbes can work to degrade herbicides. What I want to talk mainly about is the importance of microbial breakdown and what gives us better conditions. And again, it's basically warm and wet. So favorable moisture, and again, just ballparking 50 to 80% field capacity soil is what we're shooting for optimal microbial breakdown. Drier soils, they're not going to be as active. If it's too wet, it's usually anaerobic conditions, and these microbes do need some oxygen to break down herbicides as well. So basically 50 to 80%. Temperatures, about 80 to 90 degrees is the soil temperatures we're shooting for. We can get breakdown in colder soil temperatures and in higher temperatures. That's just kind of the peak or the optimal. And the other thing I'll just mention is with organic matter, the more organic matter we have in the soil, the more herbicide breakdown we'll get by microbes. So again, just more organic matter, we tend to have more microbes within that organic matter, and it does increase herbicide degradation as well. Just looking at two of the things in chart form here, so this is moisture and microbial activity and moisture content along the x-axis. And basically, the only time we're having no microbial breakdown is when there's not a drop of water in the soil. But once we start getting, we kind of have this linear curve. And once we're at 40 to 50%, up to about 60, 70, 80, that's when we have the peak moisture for breakdown by microbes. And then again, if we get too wet, then microbial breakdown quickly slows down because it's just too wet for the microbes to work, don't have the oxygen that they need for some of these reactions. As far as temperature, it's actually quite surprising how much microbial activity we'll get at some of the temperature extremes. But in general, we typically say we want soil temperatures above 60 degrees to get some good microbial breakdown. And once we get too hot, in this case the line's at 130, really once we get above about 120 soil temperature is when the microbes really start dropping off. But I'd say what we really want, 60 to 100 degrees is where we can count on some good microbial breakdown. 80 to 90 degrees is again that peak temperature that we want for optimal microbial breakdown. So we need the moisture and we need favorable temperatures. Again, that usually occurs June through August. So just kind of wrapping up the summary here of just some of the overall processes of fate of herbicides and degradation. So there's a number of different reasons why we don't want herbicide residues. Some of them are environmentally driven. For us, we're really concerned here today about crop injury next year. So that's why we don't want herbicide residues. As far as degradation, again, just can't hit it hard enough. Temperature and moisture are the most critical. Warm and moist conditions are the best. And then the thing I'll just kind of mention that doesn't change for us year in and year out. But once we have freezing temperatures, then degradation stops. So you'll listen to Frayne earlier. Every day he's looking at market conditions. When it comes to herbicide carryover, once the ground freezes, my talk does not change until the ground warms up again in the spring. Because microbial degradation and all breakdown actually stops when the ground is frozen. So again, we deal with that every year. It was just another constant reminder of some of the issues that we'll face in our environment versus someone who farms in Mississippi and gets winter-long breakdown. So looking into 2022, based on the 2021 season, what are some of the concerns that I have as far as individual chemistries? And here's kind of a short list. I'll expand it a little bit in coming slides. But clopyralid is probably top of my mind, and we use this in wide match, Resicor, using just straight stinger. So it's in a number of different products that we'll use in corn, small grain, sugar beets. And it's a very persistent herbicide. Particular crops I'm concerned about is legumes, so field peas, soybeans, dry beans, and then sunflowers as well are quite sensitive. Next on my list will be atrazine and the group 27 herbicides. So group 27 are things like Callisto, Laudis, and corn, husky and wheat. They're primarily microbial breakdown is how they leave the environment. And so planting broadleaf crops, knowing we didn't have a lot of microbial breakdown last year, that's kind of why those chemistries are of my concern. The bottom two are really more, if I take this talk to Western North Dakota, So Raptor or beyond, which is a Mazamox, we typically don't have a whole lot of carryover year in and year out. Sulfentrazone, unless you're looking at canola or sugar beets, we don't really concern ourselves with carryover. But in low pH environments, below 6, which they're having a lot of those pop up in the western part of the state, low pH environments, those two products at the bottom persist much longer than in our high pH soils on this part of the state. Okay, so the next couple slides, I'll be covering just some general rules for herbicide breakdown and based on some chemical classes that we use quite a bit in this area. There are weed guides if you don't have one. I have 3 boxes I brought outside, so make sure you get a weed guide before you go. A lot of what I'll be covering is pages 100 to 104 of the weed guide. So 3 of those pages are pretty text heavy. 2 of them are just our tables for rotational intervals from herbicides to different crops. So just for time's sake, I've kind of listed some of the important points for each slide that I'll be on, but I bolded the ones I really want to hit on. And again, the text of this is all available in the weed guide itself. So for this slide, just a general rule for breakdown. So I mentioned microbial degradation is the biggest, and that's also very important to remember. We do get chemical degradation, however, once we get above pH of 6.8, I said chemical hydrolysis is the primary way that we have chemistry break down herbicides. That slows down or ceases for most chemistry above a pH of 6.8. So again, that doesn't change for us year in and year out. It was important when we have a dry environment and get basically limited microbial breakdown throughout the year. A couple of different classes of chemistry. So the imidazolinones are a group 2 herbicides, a Mazamox or Raptor is probably the one we use most. Pursuit also falls into that category. TPS herbicides are another class of group 2 herbicides. Chlorantzalam is first rate. So as far as what we would use from that chemistry, first rate is really the one of most importance up here. And then mesotrione is Callisto. So some of our group 27 herbicides get broken down in a couple different ways, but Callisto falls under this general rule of thumb that we have here on the slide. And so the important things for these chemistries to remember are that they are primarily broken down by microbes. They're not broken down at all by hydrolysis. Maybe a couple other chemical reactions, but no hydrolysis breakdown of these chemistries. Some of our herbicides, like famecipin is one, will actually break down in waterlogged conditions. These chemistries do not. So on a wet year where we have saturated soils, they're not going to break down just due to being saturated or those anaerobic conditions. These herbicides in particular are also not volatile, they're not photodegraded, so they're stable in the sun, and they don't leach beyond 12 inches. So some of our herbicides that leach further than 12 inches aren't really going to be available for uptake by crops. So basically, whatever doesn't run off or get absorbed by crops is available in the soil, and we need to break it down primarily by microbes with those 3 classes of herbicides there on the screen. The other important ones, so SU is sulfonylurea, things like Express, Harmony, those are short-lived. We don't really care about carryover of those ones. Chlorimuron, which is classic, so some on the Minnesota side can use that product. We can't really use that in North Dakota. That's probably the most persistent SU herbicide. Otherwise, most of this slide, we're really concerned with triazines or atrazine as far as most of the talking points on this slide, just based on the products that we use. So those SU herbicides aren't leached. They don't leach, they're not volatile, and they're not broken down by the sun. The one contrast that we focus specifically on atrazine, it will leach. So that's why we're concerned with atrazine in groundwater, for instance. And in very dry conditions, if atrazine is on the soil surface for a while, it will have photodegradation occur. So again, the classics of the world won't photodegrade. Atrazine will in dry conditions where it's on the surface. These chemistries, however, are primarily broken down by hydrolysis. And again, hydrolysis ceases above a pH of 6.8 for these chemistries. So that's why, in general, if you look at our geography versus more southern states, we're limited on rates, and we just don't use a whole lot of those types of chemistries, but we do use atrazine just at lower rates compared to southern Minnesota might be able to use 2 pounds of atrazine. We never dream of that because we don't get the breakdown. So there is some microbial degradation that occurs, but it's slow. So in general, year in and year out, we're primarily microbial degradation, but it's slow anyways, much slower on a dry year. A couple other individual active ingredients I want to point out here. So again, I mentioned clopyralid earlier. Some of the reasons we're concerned with it, its half-life is relatively long, so a 40-day half-life in the soil, and it's only broken down by microbes. That's the only way to get clopyralid basically out of the environment, is microbial degradation or uptake by crops or weeds. Would be really the other way. So that's one of the reasons we're concerned with that. If you kind of dig into any label that has clopyralid in it, we're going to be much more concerned with carryover on low organic matter soils, again, because there's just fewer microbes available. And so if it's only broken down by microbes, that's the primary concern on low organic matter and sandy soils as well, compared to higher clay content, higher organic matter. Another one of concern, so pyrosulfital, which is in husky, is a group 27 herbicide. Again, primarily broken down by microbes. It doesn't photodecompose, and there is no chemical hydrolysis. So again, we really need those wet and warm conditions for breakdown of that type of product. Half-life, this is kind of a range that I can find in the literature, but basically 5 to 31 days. Longer half-life on coarse soils, again, because it's primarily microbial degradation. And the last one is tempotrione, which is lautus, that we use quite a lot. In general, less carryover concern compared to Callisto, mesotrione type products. But again, this is primarily broken down by microbes. So we really need those warm, wet conditions for breakdown of that type of product as well. So the remaining time here, I want to point out really 3 different products and some of the literature, if you look at their rotation interval requirements on the label, and some of my thoughts around those going into 2022. So I pulled from the wide match label, which is clopyralid is the active ingredient of concern, and pyroxpyrotestosterone. We're not concerned about styrene carryover. So on the label itself, and I know you won't read it, so I'm going to read it to you. This box here, it's a bunch of different crops with a 10.5-month rotation interval. Field pea has a little footnote where it says for rotation of field peas in 10.5 months, precipitation must be greater than 7 inches during that time following application, and greater than 5.5 inches between June and August following application. So field pea would probably be the most sensitive crop on that label that we can rotate to, at least at the 10.5-month interval, has that footnote requiring a lot of rainfall June through August again, because that's when the soil temperatures are typically warm. That's when we get microbial breakdown of the clopyralid in that product. So if you look at rainfall totals across the state, so you can generate these maps for your desire on the NDON website. I know Darryl Richardson will tell you that the individual numbers represent that station, and especially with the 2021 rainfall pattern, you can be a mile away and have a completely different experience. But I want to point out 2 stations that I had quite a bit of research at this past year, so I'm familiar with the rainfall patterns. That 4.73 on the screen is Prosper, and the 7.23 is Fargo, the campus location, June 1 through September 1. And so, Prosper location did not have 5 inches of rainfall in that period, so we couldn't rotate to field pea based on the label. The label was the law. Fargo location, we could. If we add in September, now that Prosper location is 7.88, so about 3 inches of rain in September. And so we did get enough to meet that 7-inch total for the overall requirement, but not having 5.5 inches in June 1 through August 31 basically means following that label we shouldn't plant field peas. The warm temperatures we had in September did help break down, but I'd still be concerned going something like field peas in that type of situation. 2 more products quickly. So it's just similar story with Rescor, which is clopyralid and mesotrione. The thing I'll point out here, if you look into the label, it's 15 inches of rain is required if you have more than 2% organic matter. If you have less than 2% organic matter, you basically have to wait 18 months. So make sure you read footnotes on rotation intervals as well. Last one I'm going to point out here is Lautus, which is Timbotrione, and the box there is 10 months. The footnote that I've highlighted is for dry beans and sugar beets, where it says you need to have 20 inches of rain from application till planting, or 20 inches of precipitation is what that label says, from application to planting. And when I put up the NDOM map from basically June 1 till now, precipitation totals, I can't find 20 on the map, whereas other years we could. So if you're planting dry beans late May, maybe we'll get up to 20 inches from April and May rainfalls. Sugar beets that we'll be planting soon after the ground thaws, not at 20 inches. So it's going to be a pretty risky proposition for some areas. So to just summarize some overall points of the talk today, so a lot of these label restrictions you might see, I mentioned 10.5 months. 2022 is not going to be the year to test that rotation restriction. So some years you might plant at 10 months after application and get away with it. This is not the year to try that because of the overall dry conditions. So make sure you look at those rotation restrictions. Again, field-to-field variation is very hard for me to stand here and say and make broad claims about what happened 2 miles away if I got 2 or 5 inches more rainfall than 2 to 5 miles away. So it's really good if you know your rainfalls at individual fields or can at least ballpark it very closely with some of the herbicides you applied and some concerns you might have on a field-to-field basis. Overall, yes, September did help. So the warm, wet conditions in September, we probably got more breakdown this September than the last 10 Septembers combined, maybe, because of how warm and wet we were. So did help, but we would have preferred it to be that wet in June and July for peak breakdown. If you do conventionally till, tillage does help dilute whatever residues are left in the soil, so just have to put a little remark in there about that. The last thing I'll just mention, bioassays, which again is really taking soil from the field of concern, putting that in a pot, planting the crop you want to grow, and growing that in a greenhouse if you have access, or kind of under a grow lamp within your house. And if you can create crop injury in that system with the soil that you want to plant a crop into, it's a good indicator of if you're going to have field-wide crop injury. So bioassays can be useful. In many cases, they are cheaper, and in some cases more reliable than lab analysis. And so the one I'll continue to pick on, we can take a soil core, send it to a lab for analysis, and we'll get results that say 4 parts per billion clopyralid in the soil. And clopyralid is the one I pick on because no one knows what that actually means biologically for a crop next year. Things like atrazine, we kind of know what a soil result means. Clopyralid, no one's going to tell you what that actually means, and the lab certainly doesn't tell you. So I would save money on testing for clopyralid in the soil. Bioassay is actually far more reliable for that chemical. So I think I left a couple minutes here for questions maybe. If you're into podcasts, I have one. We have a whole 30-minute episode with one of the premier guys on herbicide degradation. Test out a couple episodes if you want. Not every episode will be for everyone, but certainly different ways for information delivery if you like podcasts. And then, yeah, there's where all my contact information. QR code brings you to an electronic version of the weed guide.
Are there any questions? We have time for one.
Yeah.
No-till, how will that affect breakdown?
How will no-till affect the breakdown of chemical?
Yeah, so how does no-till affect the breakdown? And that's one of those, it's a very complex process. So in general, so you can't dilute the herbicide with tillage. So for some of those, you're going to have a little bit increased risk, but you're probably going to have a little bit more organic matter. And if you have a cover crop in the system, those cover crops will also absorb any free chemical that's in the soil solution as well. So no-till without cover crops, I'll say no-till with cover crops, a little bit more not breakdown, but removal of the herbicide from the system than if you don't have a cover crop. But in general, if you look at potentially cooler soils, then that'll slow down breakdown a little bit. But also better infiltration, more herbicide will potentially leach away from a concentrated zone. So it's a pretty complex question to answer, but in general, a little bit less breakdown than conventional